This video is going to be on the integration of metabolism. I drew the pathways and how they're all connected. So in the fed state, we're going to eat glucose. It's going to go through glycolysis, which I have in, it's going to go in this direction, it's this color, to turn into pyruvate. Pyruvate oxidation will occur, where pyruvate will turn into acetyl-CoA. Acetyl-CoA will go through the Krebs cycle to produce NADH and FATH2. Those will go to the electron transport chain to produce energy. When we're in the fed state, we also store glucose as glycogen in the liver and muscle. So that's glycogenesis. What else? In the fed state, we're also producing, we're doing the pentose phosphate pathway, where when G6P is produced in glycolysis, it'll produce the ribose sugar and NADPH. The ribose sugar needed for purines and pyrimidine synthesis. And those products will go back into glycolysis. What else? There's a lot more catabolism pathways. So glycogenolysis is cutting glycogen into glucose. In fasting, the liver can make ketones by turning acetyl-CoA into ketones in ketogenesis. Right here. We can break down ketones back into acetyl-CoA, which is ketolysis. We can, in the fed state, we can turn acetyl-CoA into cholesterol, which is cholesterol synthesis, and then we can turn cholesterol into bile and steroid hormones and vitamin D. In the fed state, we can turn acetyl-CoA into fatty acids, and then put fatty acids and glycerol together to make a tag. In the fasting state, we can break down tags into glycerol and free fatty acids. Glycerol can do gluconeogenesis, and fatty acids can do beta oxidation to turn back into acetyl-CoA. We can also do tag synthesis starting with glycerol or DHAP. We can also synthesize glycerol phospholipids from glycerol and DHAP. Glycerol phospholipids are phosphatidylinositol, serine, ethanolamine, and phosphatidylcholine. We also have all of our carbon skeleton pathways here, where we're breaking down amino acids into intermediates of the Krebs cycle or acetyl-CoA to be turned into ketones, or pyruvate to produce glucose. What else? We have when we break down proteins, we have the urea cycle happening. Yeah, that's how they're all connected. So here is just the pathways with their rate limiting enzymes in gray, and then what activates them and what inhibits each pathway too. Mainly this quarter we focused on lipids and proteins. There's a lot occurring in the fed state. Fed state is up to 3 hours post-meal. So we eat sugar, fat, protein. The increase in glucose in our blood will cause an increase in insulin and a decrease in glucagon. Glucose will travel throughout the blood and go to every organ. It'll go to the liver, it'll go to the brain, it'll go to the red blood cells, it'll go to muscle, adipose tissue, other tissues, but it has a different job in each. So the main energy source for our brain in the fed state is glucose. So we'll do glycolysis to turn glucose into pyruvate. We'll do pyruvate oxidation to turn pyruvate into acetyl-CoA, and then we'll put acetyl-CoA through the Krebs cycle to produce ATP. Red blood cells always use glucose no matter what, so glucose will do glycolysis, turn into pyruvate, and then it will do lactic acid oxidation and turn into lactate. Glucose will go to the liver and do a ton of things. It'll be the liver's energy source in the fed state, so glucose will turn to pyruvate through glycolysis. It'll turn into acetyl-CoA through pyruvate oxidation. Then it'll go through the TCA cycle to produce energy. And then we'll also turn acetyl-CoA into fatty acids, and then combine those fatty acids with glycerol to make a tag, and we'll transport that tag through a VLDL. And then we'll drop tags off at adipose tissue to be stored for later. If we just eat fat directly, fat will be transported into a chylomicron. Chylomicron will travel through the lymph, through the blood, and then just drop off tags at adipose tissue as well. Glucose can also go to adipose tissue and be made into tags too, or it'll be used as energy for adipose tissue too. And glucose will go to the muscle. Oh, I forgot to mention, in the liver, glucose is stored as glycogen for later, so glycogenesis. Glucose is going to the muscle to be stored as glycogen for later, but then it's also going to be used as energy, so it'll go through glycolysis, turn into pyruvate. Pyruvate will turn into acetyl-CoA. Acetyl-CoA will go through TCA cycle to produce ATP. When we eat proteins, we break them down into amino acids. The liver will do protein synthesis. Protein will also go to all of our tissues and do protein synthesis as well, because we're in the fed state. Fasting is 3 hours to 2 days after a meal, so it's a huge range of time. So we haven't eaten, our glucose plummets, Insulin plummets as a result, and glucagon rises. The main energy source is coming from tags undergoing lipolysis in adipose tissue. So tags will be broken up into glycerol and free fatty acids. Free fatty acids will go to a bunch of other organs to be used as energy. Most importantly, it'll go to the muscle to be used as energy and the liver to be used as energy. But then the liver can also turn fatty acids into acetyl-CoA through beta oxidation, and then acetyl-CoA into ketones through ketogenesis, and send those ketones to be used as energy in muscle. The tags, like I said, are being broken down into fatty acids and glycerol. Glycerol will be sent to the liver to be used in gluconeogenesis. Proteins in the muscle will be broken down into amino acids, and amino acids can be used in gluconeogenesis. Red blood cells are always using glucose as energy, but once they do glycolysis and make pyruvate, pyruvate can turn into lactate, and then lactate can be reused in gluconeogenesis. The brain is using primarily glucose in fasting. It'll use some ketones, but it's using glucose as energy, so it'll put acetyl-CoA through the Krebs cycle to make ATP. Hi, I'm videotaping. So the liver first in fasting, two things are happening at the same time. Liver glycogen is going to be broken down into glucose glycogenolysis, and that starts 2 to 3 hours after a meal, and that continues until the liver runs out of glycogen to about 30 hours. 4 to 6 hours after a meal, we start during gluconeogenesis, so that's when we start turning glycerol into glucose, amino acids into glucose, and lactate into glucose. So I remember GAL for glycerol, amino acids, and lactate. Those are the non-carbohydrate sources that are used for gluconeogenesis in the liver. It's important to remember that in fasting, once again, to maintain blood glucose levels, it's going to be gluconeogenesis in the liver and glycogen. Muscle glycogen never contributes. It gives them muscle energy in fasting and starvation, but it never contributes to blood glucose because muscle lacks glucose 6-phosphatase, and that's the enzyme that's needed to turn glucose 6-phosphate into glucose to let it out into the blood. Starvation is 2 or more days after a meal. And I'm filming.
You can't talk.
How do I cut it out of the video?
Can you pause it?
I don't think so.
Okay. Well, tomorrow night I'm gonna meet up with Sophia and Jerome. And she's gonna take video of me training Jerome. And then she said her friend Gracie can be another person that I train, so that we have male and female. And so I'm gonna do that tomorrow at 8. Okay?
In the morning?
At night.
Oh, at night. Okay.
That's all I had to tell you.
Okay. Sorry for the pause. All of my followers. Just kidding. I have like 1 follower. Starvation is 2+ days after a meal. Glucose is still low because obviously we haven't eaten anything. Insulin's low because of the glucose being low, and glucagon's even higher. Cortisol is also going to be high, and epinephrine too. Most importantly, glucagon though. tags are still broken down through lipolysis into glycerol and fatty acids. Glycerol is still a big part of gluconeogenesis going on. At this time, our liver glycogen, is gone, so it's mainly gluconeogenesis that's providing the blood glucose maintenance. The fatty acids from tags will still provide the liver with energy now, and they'll still be converted to ketone bodies, but the ketones are sent to the brain. So in starvation, the brain is going to start using ketones so that it saves glucose for the red blood cells, because glucose is all the red blood cells are able to use. The red blood cells are still going to send its lactate back to glucose for back to the liver for gluconeogenesis. Protein degradation is going to slow down because we want to hold on to our structural proteins of our organs. We don't want to eat away at our organs or else we'll die in starvation. So we break down protein as a last resort. Muscle still provided energy from fatty acids, so fatty acids go through beta oxidation to turn into acetyl-CoA. Acetyl-CoA will go through the Krebs to make ATP. If someone's shipwrecked on an island, tags are giving you the most energy. Then glucose from gluconeogenesis. The last thing would be proteins, and never answer that muscle glycogen contributes to blood glucose levels, because it can't, because of what we said before. Let me see if there's anything else. No, that's it for proteins. Not proteins. That's it for the integration of metabolism. See you in the next video.